Okay, so let's get started again. So we'll have a meetup on how to use Git soon, so you guys will get a Doodle link below. Let's go back here. Right, so now we just ran this optimizer, but we did it a very quick run, right? We just did maximum of 3 iterations and took some default values and 20 topics. So let's review the output. So we basically are asking the LDA model that just ran, and we're using this method describe topics, and we're using only max terms per topic is 5, so it's only going to give you 5 terms per topic. Now this is really ugly. It's an array of ints and array of doubles. What does this mean? Okay, so we'll see this in a sec. So now I'm also asking a vocabulary list, right? This is if I use dot vocabulary on the vectorizer, I get vocabulary list. So here's my list. And what I can do is take the topic indices that I just found 2 cells ago, and then I can map. So those vectors you saw are nothing but terms and term weights. So I can map that pair of vectors into terms.map vocab list underscore. So this is going to give me the actual word corresponding to each term, right? So there is indexing going on. And then I'm going to zip that with the term weights, which is the second thing, right? So now running this simply gives me the actual word corresponding to the term from the vocabulary list and the weight itself. So this is just peeking into the outputs a bit more, right? So you can sort of take these things apart to understand what's in here. So this is basically what I said. So you have indices, and so we're just trying to get. So what I've done basically is topic indices of 0, first element of 0 is article, and so on. Okay. So now putting this all together, I'm just unrolling this little cell earlier, right? So now I know there are 20 topics, and topic 0, these are the 5 most popular terms: article, people, rights, just, and like, and here are the weights for these terms, okay? So, okay, I don't know, just look at it blindly, like, okay, topic 1 has picture, think, like, morality, rights. Topic 2 has some other words, I don't know, I don't really see anything jumping out at me, okay? Okay, Jesus, yeah. Yeah, I mean, so the main thing is this kind of it's not really making a lot of sense, right? It's by design, some sort of. So now let's so first of all, the number of iterations was just 3, right? And so by looking at some stuff, maybe let's start tuning this a bit more, right? So we can add stop words like article, I don't know, rights, entry, whatever you think is kind of superfluous, maybe things that would be mentioned in all these topics like said, tell, think, know, right? These were not in your list of default stop words, so we can add this. Why not? You can add more stuff. And then I can define my new stop words to be just the union of the default stop words and the add stop words list. So now I can just read, all I have to do is rerun my remover with new stop words as the set stop words argument. And I can just rerun my vectorizer. This is exactly the same as before. And converting to an D, and now I'm setting my max iterations to be more than 3 this time. Okay, so it's a, and I'm still taking my default parameter. So this will be some alphas for the Dirichlet for doc concentration and topic concentration are. I think it's just 1 over k and 1, 1, 1, I think, for the defaults. Okay, so right. So how to find what the default values are generically, right? So here are the steps. So if you want to find the default value for doc concentration, we can go to Apache Spark package root, search for ML in the search box on the top left, ML is for ML library. Then find the LDA by scrolling below on the left to ML libs clustering method and click on LDA. Then you can click on the source code. This should take you directly. Let's see if this still works. It should take you to the actual. This is why it's an open source project, right? So you can see everything. And here is the actual source code for LDA. And if we look for concentration parameter, Control F, right? Yeah, so these are your alphas for the Dirichlet parameters for the prior. So let's see, the default is so here default for online variational base is uniform Dirichlet with 1 over k, right? So k is the total number of topics. So this is also uninformative. So it's actually, what that means is you're putting such a tiny number on each alpha, which means your Dirichlet distribution will be very hot. It will be spread much more. It'll be centered at the middle of the simplex, because all of them are the same, but it also will be very hot and spread out. So if you don't know anything, this is a safe thing to go with. Okay. So, oh yeah, that's 1.6. So we should probably look at what 2.2 stuff is. Just curious. Right, because this is a Spark 1.6. If I do version. Oh, great. Probably missed something. Version. What am I doing? Is it 2.2.0 maybe? Or? Yeah. Okay, so yeah. Okay, it's still here. Okay, so give me a sec. Okay, so yeah, you can try to find what the default is for topic concentration if you want. So let's convert the ML vectors into ML lib vectors. This is just some housekeeping because of the input types that are expected. So now we have this new LDA model we are running with 10 iterations and new set of stop words, right? So now let's take a look at it. We still are looking at 20 topics. So now topic 0 is objective, physics, mechanics, play, quantum. Looks a little better at least. I don't know, similar things. Image, JPEG, file, software data. Right, looks a little more sensible, right? Space, program, Windows and drive, not really. remember, you need to recall what the original top 20 topics were, right? There was a topic about space, there was a topic about Microsoft Windows, and another one about some other Unix or something. Women soldier, yeah, something about Middle East. Yeah, it's a little better, right? Yeah, something about Christianity, maybe picking up there. Okay, so so we are getting better results, but not all the results are making sense. Right? So this is just from a different run, so your outputs will be slightly different depending on because of the initialization being random. So you can just started you off on this path, right? You can do quite a lot more. So you can there are questions about how do you choose the number of topics k. That's a whole interesting problem. In the video we saw by David, he mentions at the very end, someone asked the question, and he mentions at the very end how Bayesians deal with it. So Bayesians have a full hierarchical way of dealing with this, where the prior k itself has a prior, right? The prior comes from, let's see, Bayesian non-parametrics is very rusty, right? So let's just do this. Prior distribution for number of components. Something called the Chinese restaurant process, right? How many? No, this one sucks. Okay, let's do. Yeah, so here we go. Throw Bayesian non-parametric methods. This may be a good one. Let's look at Wikipedia. Let's start here. So the Chinese restaurant process is a discrete time stochastic process. So time is going in increments. Analogous to seating customers at tables in a Chinese restaurant. Imagine a Chinese restaurant with an infinite number of circular tables, each with infinite capacity. Customer 1 sits at the first table. The next customer either sits at the same table as customer 1 or the next table. This continues with each customer choosing to sit at an occupied table with a probability proportional to the number of customers already there, right? So it's some kind of preferential sitting process. I think the number of occupied tables basically starts, giving you, a prior on the number of components, basically. So anyway, so this is just one. There's something else called the Indian buffet process. I don't know whether it is. I forgot what it is, but I used to know. So these are, you don't need to know the details, but the idea is that there are some constructive randomized processes that will give you prior distributions on the number of components themselves. Okay, so the one way to deal with this is to actually go all the way Bayesian and bring this into the picture. I think in the practical books like this, Advanced Analytics with Spark or other stuff, they take a slightly different approach, which I think will make a lot of sense for us. You will typically hold out some of the data, right? You won't let the algorithm see some of the data, and then you'll use some kind of cross-validation. You'll do some kind of cross-validation on K itself. But what is the measure you're trying to optimize? That will depend on exactly what your goal is you're trying to do with K. Okay, so for example, these guys, if I'm going to assign you chapter 7, I think. So it's chapter 5 on anomaly detection and network traffic with K-means clustering. And if you look at, if you look at the end of this chapter, I think they're already telling you how to get some kind of a choosing K, I think on page 87. So here they are, they're not doing cross-validation per se, but they're looking at some measure of how well the data fits to a given number of components, right? So they're basically finding the mean distance from every point to every cluster center. And this value we know is supposed to decrease with more and more clusters, but then they sort of look at that profile and come up with stuff. So it depends on the problem. For the recommender system, again, this is a standard thing in books like this, the next notebook. In the recommender system, you have another parameter, which is also called K, but it's the rank of the matrix in your factorization that you're trying to use to approximate this sort of recommender matrix, like which users watch which movies matrix. Once again, there, the typical approach would be to do cross-validation, but there you're trying to hold out some of the data and then try to see if the recommender system, produces outputs, recommendations that are, the same as the held out data, right? So that's another way to deal with it. But let's kind of not go crazy here. Okay, but here, you can just change K and see what happens to the topics. So I think this whole thing simply uses the EM algorithm. So here I'm setting maximum iterations to be 100. I'm still taking the number of topics to be known 20. And this will take maybe a couple of minutes because, the EM is generally slower, and I'm also doing quite a lot of iterations. And so this thing produces something called the distributed LDA model as its output, which stores not only the inferred topics, but also the full training corpus and topic distributions for each document in the training corpus. So this is kind of what I did for the Australasian company as well, with prototyping and speed up time for the data scientists, because this will allow us to, get more insights from the output. Okay. So while that's running, I'll just show you the outputs from the previous run. So once again, we can look at described topics and max terms per topic. It gives you the same array of integers and array of doubles. And here's your vocabulary list again. And now the vocabulary list size is 6122 because of the refined stop words, I guess. And I can look at my this is the same thing. So when we do it all at once, we get our 20 topics, and we have the computer drive, card, monitor, videos. Those look like topics around computers, and encryption, convenience, space one looks good. The Microsoft Windows one looks good. This one's Middle East, I think. So I'm only looking at the top 5, right? I can look at the top 20 exactly just. Yeah. Okay, so we managed to get some good results. Okay. Yeah, anyway, depending on the exact output, so there may be still ambiguous things. So here's what you could do to improve the results further. You can refilter data for additional data-specific stop words. This is something, if you, in the featureizer, there's a whole thing called lemmatization. Does anyone know about lemmatization? This is another swear word in NLP, natural language processing. So, it's a way of, so stemming is when you take a word and, basically break the rest from the stem. So, sorry, I should find out what this. Yeah, stemming. Yeah, so this is basically when they.
The root.
Yeah, the root of the word, right? And linguistic morphology. Yeah. Yeah, so so you would maybe get the infinitive of the word or something like this. Yeah, okay, cats. The cat like, cat eat. Okay. I want you to know that I'm not an expert in NLP, but I'm not. But this is just a featureizer thing, right? So you can figure it out. So the same with lemmatization is when you make these things called lemmatization. So all of these are in the same feature extraction part. So it usually refers to doing things properly with the use of vocabulary and morphological analysis of words. Normally aiming to remove inflectional endings only and to return the base dictionary form of a word, okay, which is known as a lemma. So this is a nice many-to-one mapping from tokens to something more tight, right? So you should do that. I haven't done that, but the point is you can improve this, right? So please try that at home. And what else? You can increase the model's max iterations. Experiment with a smaller number of topics. Remember, a lot of them are about computers. So it's like 4 or 5 computer-based, like Microsoft and something else. So you don't need 20. Maybe you only need 15, and so on. So then we can sort of visualize this. So I'm, just doing a zip index of the topics, and I flat map it, and yeah, and then I'm basically getting the term frequencies and topic ID, right? So this is just from the output from the algorithm. So then what I'm calling it probability because I'm using some other JSON thing stole from somewhere. So I have this term df to JSON, and I'm collecting it, making string with end of line. So all I've done is basically made a JSON string with the term key, drive, the weight, term frequencies, weight into probability, and then what topic ID it's inferred to be in. So this essentially pumped in here gives me a D3. Okay, not like a JavaScript guy either, right? But this is just display HTML as a Databricks thing. You can pump it any string of HTML. So I'm just rolling it from scratch, right? So you could do much more if you really know D3 with data-driven documents. You can have interactive stuff and so on. But yeah, I'm basically just pumping in every little bubble through the other string we made, and this gives me this picture. Right? So if I do control minus, hopefully I can see all of it in one screen. Okay? So yeah. So here, Venus, NASA, launch, space. 1993 is kind of bogus. So the point is to show that you can improve this a lot. If you spend a few hours on it, you can do stemming and lemmatization, and without thinking too much, simply increase the pipeline with more transformers. You should be able to improve it a lot more, right? But this is really as simple as it gets. You can still see the pattern. Okay. So what I wanted you to try is basically many things. It depends on how close this is to your project as well. We could do the same kind of thing on the State of the Union addresses, remember from way back when we did the word count, and there was a PNAS paper I showed you, right? They are doing essentially, time-varying topic modeling, right? So one could start, getting into that with the same exact tools you have. What else could you do with your time to understand this better? Maybe chase some of these Wikipedia articles. In fact, I strongly recommend trying to understand the EM algorithm. It's like kind of bread and butter. Maybe try and prepare a Blackboard notes. One of you guys, I'll maybe pull you at random, maybe like Lee. I mean, you're like physics postdoc, right? So anyway, the point is this is just an undergrad textbook, right? So I had this textbook when I was a student at Cornell. This is an old book, actually. Yeah, this is called Elements of Statistical Learning. I'm looking at edition 1. I think it's 10 editions or something now. So 2001. Wow. Okay, I'm old. Right. So this is just a honors undergrad book. So I think that would be a good use of time. And yeah. Oh yes, this is very important. So what these guys do, this is Databricks. Databricks minus datasets already has this data set here. Right? But they've done a lot of the cleaning already. They've pre-processed it. And so if you, so you know, this should be here. And if you actually look at it, you know, this has been already cleaned up for you. So I think they have the topic ID and the actual string contents all cleaned nicely. So you can essentially play the game directly on it, or alternatively try to do the right steps with our raw input data we took in to get close to their cleaned version, right? Because we kind of did this chopping by to end of line. These are things you could do, and any of these things are worth, you know, presenting to a quick notebook. Okay, so let me see. I think I'm going to, you know, let you guys, you know, look at this. I'll just walk through very quickly. So this is essentially what I would call like a, you know, my own example of a business use case from my own little two-man company. Okay, it's so something we did for a client, and as I said, it was just to help them speed up, you know, like, you know, save them time for their own data scientists to be able to apply this in their pipelines for the customer telephone conversations that they had. So yeah, so and for that I really couldn't use the 20 news groups example. I really needed lots of dialogues or, you know, telephone conversation like thingies. And so I did a bunch of stuff which we can go into, but I wanted to show you the output. So I have a, so if you just, so I'm taking like dialogues from lots of movies and you know, essentially doing LDA on them. But I'm also, you know, driving blind because I don't know how many types of dialogue topics there are, you know, types of dialogues there are and stuff like that. The same thing in the actual raw data we were working with. We have no idea how many types of customer relations, telephone conversations that can be, right? And it's also an Australian company, and the accents were so thick and the transcription was crazy. So, so you know, so we didn't want to overly complicate it and do it to a point where the company's data scientists can take it from there and customize it much better for their domain. So in the end, I was kind of happy when I visualized these results, and you know, so this is basically, right. So I can say, I mean, I'm just looking at the top terms, right? But yeah, so if you look at some of these strings, it looks like, I don't know, little girl, like woman, baby. I mean, you have to look at a lot more, right? I'm just showing you the top 5, but when you look at the actual conversations, I think it kind of made sense. It was, yeah, something with, yeah, this one is my favorite, right? So these IDs are dialogue IDs. So each movie has lots of IDs for each dialogue in that movie. I love you, man. I love you too. So I thought that was cool. I mean, I didn't do much, right? I just did like naive stuff and running quickly. So anyway, there's also some other, oh yeah, fucker too. Fuck him. Are you okay? Fuck no. I don't know. I mean, it would be nice to actually see the little clips of the movies to see if it makes sense. And I have no idea if like Netflix does this kind of dialogue level, you know, topic modeling. And remember the talk by David Blay last time? He's doing collaborative topic modeling, right? Remember, one of the big problems with topic modeling is, you know, yeah, I mean, actually, one of the big problems with collaborative filtering, as you will see, is called the cold start problem, which means if you have no idea about what this user, you know, if this user has not watched even one movie, what do you propose to, you know, recommend to this user, right? That's the cold start problem. So usually you have to look into more details. That's where topic modeling can come in, and that's what David was talking about, right? Collaborative topic modeling. What will be interesting is to do collaborative, do topic modeling on dialogues, and then mix that with the collaborative filtering algorithms in the movie recommendation, right? That's the next notebook. And I have no idea if Netflix does this. So anyway, I think, I guess though, yeah, it's almost a repeat of the other notebooks. They're kind of independent notebooks. So I could, so you don't need to, run all of this. The only thing here is, it was a pain to parse this data, so it took some time. So what these guys did is, so there's 220,579 conversational exchange between 10,292 pairs of movie characters, right? It's a lot. So it involves 9,035 characters from 617 movies, and a total of 304,000 utterances. So the movie metadata came in lots of files. So this was done for some other reason. They weren't really thinking about topic modeling for this. They made this data set, right? So there's all this character metadata in different files, and all the files are separated by these weird field separators, plus, $, plus, plus. So this is when you say you're a data scientist, you're working for a living, right? Your fingers hurt, you're like, what the hell? But that's important, right? Once you do this, it's processed, and so I basically marched through all the steps as I was learning it and building it. I think this took me about 5 hours or 6 hours of my time. I was under some pressure to do this quickly for their prototyping, to speed up their prototyping at the company. So anyway, so yeah, you can kind of look at this, and if you sort of quickly look at the conversational data, what are the techniques I'm using? I'm doing the same zip width index here, and I just basically looked at the top 10, and I saw this plus, $, plus. So my regex is a bit more sophisticated now, see? So I have my regex conversion, immutable, that's the string, right? In Scala, the triple quotes is kind of solid string. And I have, /s star. Okay, how do I do this, right? Like, I'm really bad at regexing, but the way I do this is this. There is this website called regex online or something. I don't know. Yeah, regexer. This is awesome, right? So I go here and I just do Control V, drop that in, right? So then, okay, so, oops. So let me just grab my pumping in here. Maybe it's just this. I don't know. Yeah, I'm just trying to find a string. I think it's maybe, let's see what happens with this. So I kind of inverse rigged the whole thing, right? You shouldn't learn how to program from me, right? But, so I'm not sure. See, this /+3, and then I'm escaping the $+3, right? So this thing is clearly trying to catch something here, right? And I think I'm trying to catch the stuff inside the parentheses here. Or maybe I'm missing I need a thing, I don't know. Okay, so I'm not exactly sure what line, but I basically did it like this, right? So you can reverse engineer this whole thing. So let's see. So this is /* w plus. Let's just kill this. Okay, you see. Okay, so I now know this is a match of the +++ star. I have group 1, group 2. So I'm basically, you can put the regexes here and try to actually do this dynamically. So This is kind of what I'm doing for lots of things now, fast. I used to do this like on the shell and was like a couple years ago, but this is way easier. Okay, so basically that's the main thing, and then the rest is, there are a couple other little tricks. So, you know, now your closures become more complicated, right? So I'm mapping and I'm doing, oh yes, this is a really good pattern to know, right? So this is a success failure pattern where I'm doing things a bit carefully. So this is kind of what you would want to do in real life. Like you will want to make sure that you're catching things. So the exceptions that are not parsed by a regex are actually flagged and kept for downstream analysis by the developers, right? Because they need to probably look at what lines didn't regex under the current regex, and then maybe correct the regex or escalate it back to the guys who generated the log lines. So that's the other thing. What else is interesting here? Yeah, it's a lot of work. Okay, so just look it up. But that's what you'll do. The rough guess is 80 to 90% of the time you'll be doing ETL. You'll be doing stuff like this to suck data from some new format. Yeah, and okay, yeah, it's more involved, right? Because I now have to take the line and movie data, and there's another regex for the movie metadata. But at the end of the day, yeah, you have movie IDs, movie titles, movie years, and then the lines data actually has the various dialogues here, and then you simply, dialogues with lines. It's basically, I think, what you're going after. Here's the text. So the line ID, movie ID, character name, text, movie title, movie year, and then just parsing that into conversation ID, and now these become my documents for, each dialogue is my document for downstream LDA. And once we are here, it's just the same thing. Exactly from step 3 onwards, it's the same game, okay? So have fun with this. Tomorrow we'll do alternating least squares and get into the most vanilla recommender system, okay?